Hello, this video covers section 11.3 from your textbook, and it's all about quadratic functions. We spent the last chapter, chapter 10, talking about quadratic equations, and now we are going to talk about quadratic functions. And we've talked about functions a lot this semester. This is just a new type of function. We're going to talk about graphing quadratic functions. We're going to talk about solving some applied problems relating to quadratics, and I wanted to start out with having you pause the video and, as a warm-up, state what is the vertex for each of the four graphs that you see here: graph 1, graph 2, graph 3, and graph 4 in your notes. Go ahead and just take a few minutes, pause the video, and write down what the vertex is. Alright, welcome back. You should have been able to tell what the vertex is for each of the four graphs. You could have told the vertex by both looking at the function and seeing what kind of shifting is going on, and then you also could have told what the vertex is just by looking at the graph and finding the point. For example, if I look at the function, we know that when it says plus 3 here, that means that we have a shift left by 3, and when it says minus 4 here, we have a shift down by 4. So if I start at 0, 0 and I go left 3, and down 4, we can see that gives me a vertex of negative 3, negative 4. And you can do something similar for the next one. The next one, you should see that it's on the opposite side. This has a vertex of 3, positive 3, negative 4. And then the next one has a vertex at right here, which is positive 2, 3. And then the last one has a vertex at negative 2, 3. Now there's one thing that all of these examples have in common. All the vertexes have in common. And that's what I wanted you to ask yourself in this question part B. It says, what do you notice about the vertex of the equation? And what you should have noticed is that the vertex, in relation to all the other points on the graph, the vertex is the lowest point. I.e., it has the smallest y value. Of all the points on the graph. Which is significant when it comes to application problems, because in applications sometimes we're concerned with finding the smallest or the lowest point on the graph. So we're going to talk about that in just a second. Before we do that, though, let's review how we go ahead and graph a quadratic equation that's in this form by shifting. And so there's a couple things we can tell about this graph. Number one is that negative out in front tells us what? You should be thinking that it tells us that it opens down. We also know that this plus 1 here means there's a shift left 1. And then lastly, the plus 9 here means there's a shift up by 9. Alright, so if we know it shifts left 1 and up 9 from starting at 0, we know that makes the vertex right here. We go left 1 and we go up 1, 2, 3, 4, 5, 6, 7, 8, 9, which puts the vertex at the point negative 1, 9. And then there's a bunch of different ways we could come up with points, but probably the easiest way is to graph this with a graphing calculator and use the table to find some other points. So if I turn on my graphing calculator here and put the equation in, clear out that old one, let's put it in. It's negative parentheses x plus 1 squared plus 9. Or you could use the caret x squared plus 9. Either way, you're going to get the right equation. I'm going to hit zoom option 6 here. And we can see that it definitely looks like the vertex is where we expected at negative 1, 9. We can go here to our table. And you can see here there's negative 1, 9. We also have the point negative 3, 5. Negative 3, 5. And then on the opposite side we have the point 1, 5. You see that in the table? We have negative 3, 5. We have 1, 5. Come back here. We have intercepts at negative 4, 0 and 2, 0. We get this nice parabola shape. Here's the 2, 0, 1. We go ahead and put our smooth curve in here. See a nice parabola. Again, we wrote down that the vertex was at the point negative 1, 9, and we got some other points on the graph. So that's how we go about graphing this. The only difference between this and what we did before is before we called this y equals the rest of the stuff. But is there a difference between y equals and f of x equals? We know the answer to that question is no. We could also talk about what the domain and range is. What's the domain and range? We haven't done this for a while on graphs. We did it a little bit last few sections, but how do we come up with the domain and range? Remember, the domain is the x's. As I'm looking at this graph, it keeps going down, and as it's going down, it's going to the left. It's covering all the x values. Same thing, as it goes down to the right, it's covering all the x values to the right. So is there a restriction on the domain? No, it's negative infinity to infinity. What about the range, though? Is there a restriction on the range? Does it cover all the y values? Well, we've been talking about vertex here, vertexes here, and notice here it has a highest value. There's not any values that go higher than positive 9. Now, it does keep going down all the way to negative infinity, so the range here is going to be everything from negative infinity up to positive 9, and we're going to put a bracket here because we include positive 9. Now, what sets this example apart from the graphs on the previous page? We have all these graphs on the previous page. Notice that all those vertices are all minimum points, whereas here, this vertex, when the parabola opens down, the vertex is a what? This is a max value. It's the highest. It's the highest value. Okay, now we've seen examples of graphs where the vertex is the maximum value and examples of parabolas where the vertex is the minimum value. Let's go ahead and summarize our findings. Basically what we found out is that when a parabola opens upward, that means it looks like this right here. When the parabola opens upward, that means its vertex, or the y-coordinate of its vertex, tells us the minimum value. Minimum value. This is a minimum. It's the lowest point. And likewise, when the parabola opens downwards, the vertex is the highest point, or the maximum. The y-coordinate of the vertex tells us the maximum value. Minimum value. And this becomes very, very useful when we're looking at some types of application problems, especially ones involving optimization where we're trying to find the maximum of something or the minimum of something. Now before we do an application, let's just see Now before we do an application, let's see how this works with just a standard quadratic function. It says, does the function f of x equal negative 2x squared plus 3x minus 5 have a maximum or a minimum value? And how do you know? Well, very simple. How do we know? We take a look at our function. First of all, how do we know if it has a max or min value? Well, we should be able to tell by whether it opens up or whether it opens down. And how do we know if it opens up or down? Well, we look at the sign right here. Since that's a negative, it opens down. And it opens down, that means we're looking at this picture, which means the vertex has a what kind of value? A maximum value. So this has a maximum value because the parabola opens down. So the next question is, if we know it's going to be a maximum, how do we find it? And we know how to find vertices. We did this in the last chapter on the last test. We know that x is equal to what? The x value of the vertex. It's equal to negative b over 2a, or negative 3 over 2 times negative 2, or negative 3 over negative 4, which is positive 3/4. And we can find the y value by plugging that back in. It's negative 2 times 3/4 squared plus 3 plus 3 times 3/4 minus 5. This is equal to negative 2 times 9/16 plus 9/4. Just multiplying 3 times 3 is 9 over 4 minus 5. This is equal to, well, this is like 2 over 1. 2 goes into 16 8 times. So this is negative 9/8 plus 9/4 minus 5, which if we convert everything to eighths, it's negative 9/8. This is going to be plus 18/8 minus 40 over 8. Which gives us negative 31/8. So the maximum value is negative 31/8. Alright, so this problem gave us an idea of how to solve and find the maximum value or the minimum value if we're given a function, but it probably makes a lot more sense if we're looking at an application type problem. So I have a couple here on the next page. Sometimes we have to come up with a function that we have to maximize. Sometimes it's given to us. This first example, we actually have to come up with it. So let's go ahead and read through this. It says, with 36 yards of fencing to enclose a rectangular region, the dimensions of the rectangle, find what dimensions of the rectangle will maximize the area, and what is the maximum area. And the first thing that you should notice here is that it uses this word maximum, which should kind of send off some light bulb in your head that says, oh, it says maximum. That means we need to find the what? Find the vertex. And this is an application problem, which means we need to be organized. We need to go through our problem solving process. The first thing we need to do is write down what we're given. It's going to help us out here if we write down what we're given, and since this is a geometry related problem, we should probably draw a picture. We know that this rectangle has dimensions of width and length, and we also know that it has 36 yards of fencing. Now if this is a fenced in area, the fencing goes around the outside, and we have a special name in math or geometry for the distance around the outside of something. We call that what? We call it the perimeter P. So the perimeter is 36 yards. And the perimeter, if you'll remember, is just we add up the sides. So if this side is length W, then this side is length W, and then if this is L, then this side is also L. So from that, we can write that the perimeter is 36, and that's equal to two sides of length W, this side, and then add to that two sides of length L. Now the next thing about this problem is that it's asking us to find what? It's asking us to find the maximum area. Well, if we want to find the maximum area, then we're definitely going to need an equation for area. We know the area of a rectangle is what? It's length times width. And one thing I want you to notice here at the beginning is this is not a quadratic, which means in its current form, can we find the vertex? Most definitely not. We're going to have to do a little bit more legwork, so we're not going to be able to find the vertex yet. Also notice that the area is in terms of two variables, length and width, and we would like to be able to get this in terms of just one variable. And how do you suppose we're going to do that? Usually in the past we've done it by substituting. We were given something like maybe the length is 5 more than the width, and we plug it in. Here we don't have that, but we have another, what we call constraint. Not that the length is 5 more than the width or something like that, but we have the constraint that the perimeter is 36. Now, before we go ahead and try to do some substituting, we should probably make use of the fact that all these terms are even, so they're all divisible by 2, which is going to make this relationship a lot easier to work with. It's going to give us that 18 is equal to the width plus the length, which means that width is equal to 18 minus L. That's if I take this L and I subtract it to the other side. Then I get that width is by itself is equal to 18 minus L. I also could have solved for L and said L is 18 minus W. Either way, I can now take what L is equal to, the 18 minus, I can take what W is equal to, the 18 minus L, and I can plug it in for W. What do we call that? We call it substituting. We do it all the time in math. And this equation now becomes A is equal to L times, when we substitute, we put something in parentheses, L times 18 minus L. Right? That's W. W is 18 minus L. And we could then distribute. We get 18L minus L squared. And now notice we have a parabola. This is now a quadratic. which means can we find the vertex? Absolutely. Now most of the time we're used to seeing this in the form where the squared term comes first. So let's rewrite it as negative L squared plus 18L, which means now that the vertex, the x-coordinate of the vertex, or in this case L, because that's the independent variable, L is equal to negative b. That was 18L, so negative b is negative 18 over 2 times a, which is negative 1. So this is negative 18 over negative 2, which is positive 9. Which it turns out in this case that not only is the length 9, remember this relationship here, W equals 18 minus L, which will be 18 minus 9, which is 9. So what are the dimensions? The dimensions that maximize area are 9 yards by 9 yards, which gives a maximum area of 9 times 9, or 81 square yards. Okay, so that's one example of a optimization problem. Notice that we do expect this to have a maximum value because it has a negative L squared, which means it opens down. Okay, let's take a look at the next one. It says the revenue received for selling X stereos is given by the formula R of X equals negative 1/5 X squared plus 80X minus 1000. Is this going to have a maximum value or a minimum value? That's negative. It opens down, which means it will have a max value. And again, I want you to notice that it uses the word maximum, which means find the what? The vertex. And again, the vertex x is equal to negative b over 2a, negative 80 over 2 times a negative 1/5, which is negative 80 over negative 2/5. Instead of dividing by negative 2/5, let's take negative 80 times the reciprocal, negative 5 over 2. Of course, 2 goes into 80 40 times. We have a negative times a negative is a positive. 40 times 50 is 200. And we just found X, and we know that X stands for the number of stereos sold, which means we answered the first question. How many stereos must be sold to obtain the maximum revenue? 200 stereos must be sold to maximize revenue. And what is the maximum revenue? Remember, the maximum value is always the y coordinate of the vertex. So the y value, or in this case actually the r value, because r is the y value, it's r as a function of x. So in this case we want to know what r of 200 is. We're just going to go ahead and plug 200 back in. We have negative 1/5 times 200 squared plus 80 times 200 minus 1000. Go ahead and plug that in. We have negative 1/5 times 200 squared plus 80 times 200 minus 1000. Gives us a revenue of $7,000. This is the max revenue. All right, so there's some applications involving optimizing, either finding maximum or minimum. One more thing in this section is we're going to talk about evaluating the difference quotient, which is basically nothing other than a rate of change. The difference quotient, f of x plus h minus f of x over h, is used to determine rate of change because it's a change in one value over a change in another value. To be able to do that, we need to calculate f of x plus h. That's the first part of this difference quotient, and we already know how to do that. We did this earlier in the chapter. F of x plus h, we're just going to take x plus h and plug that in as our input. So it's going to be, instead of x squared, it's going to be x plus h squared plus 3, which we know is x plus h times x plus h plus 3, or it's x squared plus 2xh plus h squared plus 3. So let's keep that in our back pocket. We're going to now do the example. It says for the function x squared minus 13x plus 47, simplify the difference quotient. Well, that means again we need to know what f of x plus h is. It's going to be, in this case, x plus h squared minus 13 times x plus h plus 47. And we already know we did this part, the x plus h squared, we did that part up here in that short example. That part came out to x squared plus 2xh plus h squared. And then when we distribute here, make sure you distribute the negative as well. So this is a negative 13x and a negative 13h and a plus 47. So the difference quotient, f of x plus h minus f of x over h, becomes simply the first part here, the f of x plus h. That's going to become what we already calculated. It's going to become x squared plus 2xh plus h squared minus 13x minus 13h plus 47. Then we're going to subtract away f of x. We're going to subtract away f of x, which was already given to us. F of x is just the regular function without anything done to it. It's the x squared minus 13x plus 47. And then the whole thing is over h. Well, when we subtract away, some things disappear here. We're subtracting x squared minus x squared, so the x squareds will cancel. We're also taking a negative 13x and subtracting away a negative 13x, so those will cancel. And we have a 47 minus 47. So after doing that, what we have left is 2xh plus h squared minus 13h over h. We can pull an h out of the top, a common h. Factor out h, we're left with 2x plus h minus 13 over h. And what can happen there? The h's cancel. And if you do the difference quotient right, the h on the bottom will always cancel with an h on the top. So our final answer here is 2x plus h minus 13. And that does it. All right, thank you for your time. I will see you in class.